Hello, my name is Akin Zhang, and this is my COMP3132 Assignment 3. So to start off, we're going to import all of the necessary packages and libraries, and we're going to get this image right here. We're going to put this image inside an array, and what we find is that this is an image that is 349 by 140 pixels, and also has 3 color channels. We can do some comparison to see that the color channels in 0, 1, and 2 all have unique values. And just for reference, we can also see that this is color channel 1, this is color channel 2, and this is color channel 0. We're going to put color channel 0 into our input image array. And if we take a look at it, we can see that it is a grayscale image. So now we are going to begin our convolution layers. So convolution is going to place this smaller array called a kernel, and this kernel is going to go across the input image array. And what this kernel is going to do is it's going to take a bit of a snapshot, and that snapshot determines or can be changed by what's inside this kernel. And this helps the neural network recognize local patterns. Because we have an array that's 3 by 3 and we want to center it on the very left corner, we're going to need to introduce some padding. So we end up with 2 extra rows, 2 extra columns, and what this culminates in is a 1 by 1 border around the original array. Here's our for loop to iterate through the input image array. You can see we have -2, 0 -2, and 1 -2. And what this means is that the kernel will always stay inside the bounds of the padded array while being able to be centered on every single pixel of the image. Now, once it goes through the array, the matrix multiplication occurs, and that 3 by 3 matrix is going to result in a single value, which is placed in another array. And the position of that new array is going to correlate to where the kernel was on the original image input array. So before we go through the convolution, we're going to show the image once more. And when we perform convolution, we're going to multiply the value of the image based on the kernel. And what this might result in is large negative values as well as large positive values. However, we can have this squash pixel value here to make sure that everything returned is between 0 and 255. Okay, now we can have a custom convolution 2D kernel image. And what this is going to do is take our image, take our kernel, and it's going to perform the convolution. So we have a padded array as well as the kernel, which is chosen right here. And we have a transformed array, which is the result after the convolution. So here is the for loop to go through the input image arrays. And we've chosen the squash pixels image, or the squash pixels function to be true. So we're going to make sure everything is between 0 and 255. And then we're going to return the transformed array. So we're going to run this function. And what we can see is that if we use a kernel that looks like this, the horizontal lines are emphasized. So what you can see here is that for the areas in the array that we put as 2s, we're going to see those in our convolution arrays, whereas -1s are not going to be as emphasized. So now we're going to create a diagonal array, and this is a 45-degree one, which means it will go from bottom left to top right. And as a result, we can see that these lines are the ones that are most highlighted. We can do the same with 135 degrees, and those ones go from top left to bottom right. And what we can see is that now the ones going this way have the most emphasis. Okay, if we have an edge kernel like this is going to emphasize the top left and the bottom right most. And you can see that edges around here as well as here are going to be highlighted. If we have an edge kernel like this, we can see that the ridges are going to be the most emphasized over here. And lastly, if we have something that goes around the entire kernel here, this is going to give us essentially an outline of the image. And that's what we have over here. Okay, next we're going to take a look at the CIFAR10 dataset. So what this is a dataset that has 10 different categories for all these images. And we want one-hot labels because our values from 0 to 9, our 10 values, don't hold any inherent value. They're just going to be the different possible categories. We're going to turn the images to floats, and we're also going to normalize them. So they're ranges between 0 to 1. We have our model that consists of 5 layers, and we're going to go through what each of these layers do later. We also have our compilation with the atom optimizer. We want categorical cross-entropy because we have a categorical neural network, and we'll take a look at the accuracy metrics. So here are the 5 layers: conv2D, max pooling 2D, flatten, one dense layer, and another dense layer. We can use a custom callback class to track the accuracy for training and validation as we go through each of the epochs. Now we're going to fit our model, and we're going to see what the result is. So we can see that near the end, our training accuracy is around 91%, while our validation accuracy is only around 65%. To visualize this, we have a plotting function. And what we can see is that near the end, training accuracy is very high, but validation accuracy still stays around the same. So this does mean that we have signs of overfitting because we have a large disparity between training accuracy and validation accuracy. We can see this begin to spike at around epoch 7, where the validation accuracy stays the same, but the training accuracy begins to constantly increase. So let's take a look at each of these layers. So they are conv2D, max pooling 2D, flatten, dense, and another dense layer for the output. So the conv2D is the convolution layer. It's going to take a small chunk of the image, which is our chosen kernel, and it's going to reduce that to a single value. And what this does is it allows our neural network to recognize local patterns. What max pooling 2D is it shrinks the input from the conv2D layer by a factor of 2. And it does this by using a 2x2 window, and it only takes the highest values from the conv2D layer. This combined with the conv2D layer forms something called a convnet. Flatten is going to take the output from max pooling 2D, and it's going to multiply all those dimensions together to form a 1D vector. And this is because dense layers only take a 1D array, and that's what flatten will do. Our dense intermediate layer is where information processing happens for global pattern recognition. And it will adjust the weights as the input goes through the neurons. And at the end, it's going to produce its answers to one of the output layers. We have 10 possible combinations in the CIFAR10 database, so we have 10 output layers, each output layer corresponding to one of the categories. We're going to add another convolution layer to the model. So here I've chosen another convolution model with a convolution layer with a input kernel of 5 by 5. And what this is going to do is recognize more broad patterns throughout. We're going to compile it once more. And what we can see is that now our validation accuracy has gone up by not that much. We went from 65% to 67%. But what is a lot more noticeable is that our training accuracy spiked a lot higher. So if we compare these two before, what we can see is that the marginal validation accuracy doesn't actually represent that much. What we can see is that overfitting seems to happen a lot more quickly with this layer, as we can see that the training accuracy becomes much higher, much earlier. It also takes a longer time to train the second model. So what this means is that with extra convolution layers, it's likely that each neuron is a lot better at memorizing instead of actually predicting. So to remedy this, we're going to add a dropout layer. So here we have our dropout layer. We want to put this in between the intermediate layer. And we only have one intermediate layer, so we're going to place it right here. We have a parameter of 0.5. That means half the neurons will not contribute to the output layer. And this is randomly determined every epoch. Once again, we're going to compile this new model. And what we can see is that the training accuracy drops, but the validation accuracy increases. So what's happened here? Well, dropout layers randomly select neurons in the dense layer during each training epoch to be unable to contribute to the output layer. This causes the neural network to prevent memorization, as each neuron may not be available during each epoch. The result is that during validation, the neural network is more robust because the neurons are more generalized, culminating in a reduction of overfitting. During the end, in validation, each neuron is available to be used. You can sort of think of it like if you were to train your arm. Let's say you normally use your arm, your entire arm, to carry a bag of groceries. But if you decided to, say, isolate each muscle and train them individually, now when you use your arm, it's going to be a lot stronger than if you were to just, say, train your arm regularly. Okay, this concludes my COMP3132 Assignment 3.